In this lecture, we'll discuss separate chaining, which is a collision resolution technique. In this technique, we'll maintain linked lists for records that are mapped to same hash address. So here, each slot of hash table will refer to a linked list of all records that have same hash value. Any index I of the hash table will refer to the linked list of all records that have hash value I. Now let's understand with the help of an example how we can resolve collisions using separate chaining. These are our keys. We have used this hash function and we have this hash table of size 7. We can see that the keys that are mapped to same location are stored in a separate linked list. These two keys are mapped to location 0, so they are in this linked list. These 4 keys are mapped to location 1, so they are in this list. This key is mapped to location 2, so it is in this list. These 3 keys are mapped to location 4, so they are in this list. And this key is in this list. So keys are stored in respective lists depending on their hash addresses. Now let's see how insertion, deletion and searching is done. For inserting a key, first we'll evaluate the hash function and get the hash address. Then we'll insert the key in the beginning of the corresponding linked list. For example, suppose we have to insert this key in this hash table. First we get the address. It is mapped to location 4. So it will be inserted in this linked list. We insert it here in the beginning of the list. Now let's come to searching. For searching a key, again we'll evaluate the hash function and get the hash address. And then we'll search the key in the corresponding linked list. For example, suppose we have to search this key. We get the hash address. Hash address is 1. So we'll search for this key in this linked list only. Now for deleting a key, first we'll search the key and then we'll delete the node that is holding the key from its linked list. Now these linked lists are referred to as chains, and we have a separate chain for keys having same hash address. So this technique is named separate chaining. Now let's analyze the performance of these operations. The time to compute the hash address of a given key is constant, and we are inserting in the beginning of the list. So insertion is a constant time operation. In the case of searching, finding the hash address again takes constant time, but searching through a list takes time proportional to the number of items in the list. So the searching time depends on the length of the lists. If the lists are short, searching time is less. But if lists become long, then it takes more time to search a given key in any list. If the distribution of keys is uniform, it has been shown empirically that the average number of keys per chain is roughly proportional to the load factor. So on an average, the list length is equal to the load factor. We have seen that the load factor is defined as a ratio of number of records and the size of the table. In case of unsuccessful search, we have to go to the end of some list. So we'll have about lambda comparisons. For successful searches, we go about half the way down some list. So on average, the number of comparisons in a successful search is this. So we can say that the runtime complexity of separate chaining is this, where this lambda is the load factor. The worst case is when all the keys hash to the same chain. And in this case, the search time becomes order of n. This method, separate chaining, is useful in dynamic situations where the number of the keys is not known in advance. Hash table never overflows. You can always insert more elements in the chains. Another advantage of separate chaining is that deletion is easy. No special flag values are required. To improve the retrieval performance, we can maintain the lists in sorted order. This is useful if there are much more searches than insertions and if most of the searches are unsuccessful. The main cost of separate chaining is the extra space required for maintaining the linked lists. Now let's see how to choose the table size in separate chaining. This method is generally used in cases when the number of records is not known in advance. So the choice of table size depends on the memory available. If table size is too large, then there will be many empty chains, thus wasting large area of memory. If table size is taken too small, then the chains will be too long and the searching will take more time. Generally, table size is chosen such that n by m is equal to 10, where n is the number of records and m is the size of the table.